Hello everyone, welcome to the lecture series of 8085 microprocessor. In the previous lecture, we have been doing this additional instructions. We did this LXI, LDA, STA. Now in continuing with this additional instructions, we'll move further. So the next instruction is move M, R. This one, which we are saying now, this is move M, R. So this move M, R is a 1 byte instruction. It stores the contents of the specified register into the memory location. So like let us see with an example. Like suppose if we write, now the examples, like if we write move M, A, then the contents of register A are stored in memory location. Then if we write move M, H, or any other register, let us say M, B, so the contents of register B are transferred to the memory location. Now memory location, there are 65,536 memory locations. So where does the data goes to? Which memory location the data goes? So suppose if we write the instruction LXI H 8040, okay, so in terms of memory location, for case of 8085, the starting memory location is of course 0000, then we have 0001 and so on, and it goes up to FFFF. So there may be 65,536 memory location, that is 64K, what we say the memory capacity. So there may be so many number of memory location. So suppose somewhere here, maybe I'm not trying it to scale, somewhere here we may have this 8040, suppose, okay, and then of course here we have 8041 and so on and up. So suppose if register A contains 13H, okay, and if we write the instruction move M, A, okay, so this particular instruction move M, A, it transfers the contents of register A to the memory location. Now which memory location? Which is pointed by HL register pair. Now in the previous lecture we saw that LXI H, it will store the data 80 in H and 40 in L. So here H contains 80, L contains 40. So this particular instruction move M, A, it transfers the contents of register A to the memory location which is pointed by HL register pair. So this 8040 is here, so this 13 it gets transferred here, okay, the data 13 it goes to this particular memory location, okay. And suppose if we have let us take one more example. So we have some memory location here, 8050 and so on, okay. So if we write the instruction, suppose LXI H 8050, and if suppose register C contains 17, and now if we write the instruction move M, C, so the contents of register are transferred to memory location which is pointed by HL register pair. So 17 it gets stored here, so 17 comes here, so we get 717 here, okay. Now whenever we are talking of M, of course M is a memory location which is always pointed by HL, okay. So we can store the data from any register to the memory location which is pointed by HL. Similarly, we also have the other instruction. Suppose this location 8050, suppose it has 717 stored here, and we have this 8050. Now suppose if we write the instruction move D, M, so this instruction it transfers the contents of memory location to register D. So this memory location is pointed by HL register pair, so this contains 17, so D 17 gets stored in register D. Similarly, if we write move E, M, same way the contents of memory are stored in register E, which content which are stored, which are pointed by HL register pair. So this 17E becomes 17. So that's all. Next we have the instruction LDAX. So LDAX, the full form is load accumulator indirect. In the previous lecture we did LDA. So LD, the full form of LDA is load accumulator direct, and this LDAX is load accumulator indirect. So there are two instructions, LDAX, LDAXB and LDAXD. There is no LDAXH. So we only have two, LDAXB and LDAXD. So this is a 1 byte instruction. Okay, it stores the contents of the memory location to register A, and the memory location are specified by either BC or D register pair. Let us see with example. And one more, we have this STAX BSTAXD. This is also a 1 byte instruction. It does the opposite of LDAX. So STAX it stores the contents of register A to the memory location specified by either BC or D. So let us see one example. This is actually not LDAX, it should be STAX. Okay, so suppose we have some memory location here. I'll use this. So suppose we have somewhere here 8040 somewhere here, and let us assume 13 is stored here, and then after some memory location we have some here 8050. Okay, and here we have suppose 15. Let us see the example of LDAX first. Now if I write LXIB 8040, now because of this LXIB, 80 gets stored in register B and 40 gets stored in register C. So because of this, register B will has 80 and C has 40. Okay, so next what we do, suppose now if we write the instruction LDAXB, so this instruction, it tells the microprocessor to store the content of a memory location to register A. So which memory location? Now because we are getting here B, so it means whatever is in B and C, okay, that memory location, the BC contains 8040, so 8040 it contains 13, so register A will contain 13 will get stored in register A because it is pointed by BC register pair. Now similarly, suppose if we have let us take another example now. Suppose if we have LXID 8050. Okay, now because of this 80 will get stored in D and 50 in E, and if we write LDAXD, so this instruction, it tells the microprocessor to store the data from the memory to register A. Now which memory? The one which is pointed by DE register pair. So D points to 8050 and 8050 it contains 15, so A will become 15. So this is how this LDAX works. Remember that the destination is always register A. We cannot store the data from DE or BC pointer from to any other register other than A. HL, okay, we can store from HL pointer to any other register, okay, with using that instruction R, M, but this is only for register A. Now similarly, we have, just as we have done LDAX, we also have STX. Now suppose if I write this instruction LXIH 8 sorry, not LXIH, we have LXIB, okay, 8040, and LXID, it is suppose 8050, and if we write MVIA 1010, we are storing 10H. Now suppose if I write LDASTAXB, so what this STAX is, now with LXIB we know this B and C become 8040, DE becomes 8050, okay, and of course they also become the memory pointer. This is BC here and DE is here, okay. Now with MVIA 1010 gets stored in register A. Now suppose if I write STAXB, now this instruction will store the content of register A to memory location. Now which memory location? The one which is pointed by BC. So BC is pointing to 8040. So of course this particular data, this will the content of register A, which is 10, will get stored here. Okay. Now suppose if I write here STAXD, so this instructs the microprocessor to store the content of register A to memory location. Now which memory location? Because here it is D, so it will store to DE pointer. So DE pointer is here, so of course this will also become 10. So this is how we have LDAX and STAX. Now one more instruction is left in this particular list, the last one. This is MVI M, 8-bit. Now of course this is move immediate into memory the 8-bit data. This is a 2-byte instruction. Okay, this is used to load the 8-bit data into the specified memory location, and the memory location is specified by HL register pair. Let us see this actually. Just move, we don't need this. So suppose if we have at this point we have 8040, okay, and if we write LXI H 8040, so this H, that is M memory pointer, is actually here. So we write this HL pointer as actually M. Now suppose if we write here MVI M, 12H, okay, 12H. So this particular instruction, it will store the data 12H in memory location. Now which memory location? Which is pointed by HL register pair, so 12 gets stored here. Okay, so whenever we are talking about M, so M is a memory location, but it is always pointed by HL pointer. Okay, so we just saw some additional data transfer instructions with respect to memory. Now we'll see some more additional instructions. Now these are concerned with some arithmetic and logic instructions. So the first instruction is add M. So this is a 1-byte instruction. It adds the contents of register A with the contents of memory location, and of course the memory location is pointed by the register pair HL. So let us see with this example. Now we'll use the same here. Sorry. So suppose if we have some memory location here 8040, suppose 033 is stored in this location, and we write LXI H 8040, and then if we write MVI A 03, let us take 02H, then if we write add M. Now this instruction add M, what it will do, it will add the contents of register A with the contents of memory location, which is of course pointed by HL register pair, and store the result in register A. So A is of course 2, so this is 02, and the content of memory location which is pointed by HL is 8040, so this is actually 3, so this is 03, it gets stored in register A, so A will become 5. A will become 5. Okay. Similarly, just as we have add M, we also have sub M. So sub M is of course in similar way, like if we have LXI H 8040, and if we write MVI A, suppose 05H, and so if we have 8040 here and it contains suppose 03. Now if we write sub M, now this instruction sub M, it subtracts the contents of it does the subtraction A minus M, where it is pointed by HL register pair. So it performs this particular operation, and stored result gets stored in register A. So this A equal to A minus, so A is actually 5, and memory location contains this memory location is pointed by HL, so HL is 8040, and it contains 03, so 03, so this becomes 02. So this result gets stored in register A. Now after this there are some more instructions, but I will just go for this because we are doing this. I will just show some logic instructions. Now suppose if 8040, if it contains let us assume it contains 10H, okay, 10, or let us take some different data. Suppose it contains 29, okay, 29, here 29 is stored. Now if we write ANAM, so this particular instruction, it logically ANDs the contents of register A with the contents of memory location which are pointed by HL register pair. So this is actually, we are doing A equal to A and M, okay. So M of course is pointed by HL register pair. Similarly, just as we have A and A, we also have ORAM, okay, we also have XRAM. So this will logically OR the contents of A with memory location pointed by HL pair, and this logically XORs the contents of A with register with memory location which is pointed by HL register pair. So these are the few instructions. We will see some more instructions now. Okay, so in the previous slide, whatever instructions we saw, add M, sub M, ANAM, XRAM, etc., they all are 1 byte instruction. Now next we do this INRM and DCRM. We will see this instruction. So INRM, of course, this is a 1 byte instruction, and it increments the contents of the memory location pointed by HL by 1. And DCRM, it decrements the contents. It is also 1 byte instruction. It decrements the contents of the memory location pointed by HL by 1 unit. So let us see this example. Okay, we have this. Suppose if we write LXI H8040, and suppose if 8040 this contain 29 is at 8040. Now if I write this INRM, so INRM, it will increment the content of the memory location pointed by HL by 1. So this is 29. This 29 will become 30. 29 will become 30. So 29 will become 30. And if we write this DCRM, it will decrement by 1. So this 30 will become 29 again. Okay. Next, this was regarding INR and INRM and DCRM. Now here one more instruction we'll see now is of course this INX and DCX. Okay. See, this we have already done. This number 7 ANA we already done. Okay, ANA, and we have some more instructions, ANA and then ORA and XRA. Okay, so we will directly do this DCX and INX. Okay, so this INX instruction, the full form is increment register pair. Okay, and then DCX decrement register pair. So let us see what this instruction does. So okay, now with respect to INX RP, so increment register pair, there are 4 INX instructions. One is INX B, INX D, INX H, and INX SP, stack pointer. So INX B, how it is different with respect to INRB. Okay, we have already done this INRB, and now we are going to do INX B. So what is the difference? Now before studying the difference, suppose if we have a counter, a two-digit counter, a decimal 2-digit counter. So it suppose it starts from 0 0. Okay, if it is a decimal counter, it will increment. If it increments by 1, you will get 0 1, then 0 2. Okay, it will continue 0 3 dot dot dot, then 1 0 and dot dot dot, finally 9 9. After 9 9, it will again reset and come to this count 0 0. It will restart from 0 0 again. Now suppose if we have a 4-digit counter, 4-digit. So we have this 4-digit counter. Now if we increment this counter will count, the first count is 0 0 0 1, then next is 0 0 0 2. It will continue. Okay, and maybe around we get 0 0 9 9. but after 0099 what will happen, it won't reset, it will actually become 99 will become 100. So whatever carry, it passes to the next digit. Okay, so this is a difference. This is actually a 2 decimal counter, this is a 4 not 2 decimal, 2 digit count, this is a 4 digit counter. So the same thing is actually happening in the case of INR and INX instruction. INR instruction, this INR instruction, it considers register B to be a 8-bit register. So when if a register B contains, suppose B contains 00, if we give the instruction INRB, it will become 01, then it will become 02, and so on. It will go on incrementing as long as we give INR instruction. Now with respect to INXB, it considers register B and C as a 16-bit single register. So when we go on incrementing, it will increment in such a way that it will consider this B and C as a 16-bit number, not a single B as a 8-bit number, a 8-bit register. So it will go on if we go on incrementing, it will go on incrementing until, suppose if we get 00FF, because it is a hexadecimal register, this hexadecimal numbering system is used in this register. So after FF it will become 0100. So this is how it works. Okay, the carry from F is passed to the next bit, so it will become 00. The last count which we get will be FFFF. Okay, and it will again reset to 00. So this is the difference between INR and INX. Okay, so there are only 4 INX instruction. Okay, INX is used for incrementing the register pair. So as we have INX RP for incrementing the register pair, we also have DCX RP. So it decrements the contents of the register pair by 1. So there are of course 4 DCX instruction: DCXB, DCXD, DCXH, and DCXRP. So this DCXSP. So this particular DCX instruction, it considers, for example, this one DCXB. DCXB considers register BC as a single 16-bit register and decrements the contents of that particular register pair by 1. Okay, so that's all for this particular session. We'll do some programs based on the instructions we have done in this particular session. Please go through it again and again, because there are some confusing part is there, because it is related to memory and memory pointer. So you must know which instruction to use where. Okay, thanks for watching.